really excited about to talk about exoplanets and the habitability related to origins. And hopefully, by the end of this talk, you probably would be convinced completely that there's a good habitability case. I know this is a tough crowd for origins. So let's see how I do. Oops, excuse me. How do I advance a slide? I'm trying to advance a slide.
No, I think it's that other one, the big one.
That one. That one. Oh,
green
okay.
button.
All right, thank you. Okay, I'm going to start with a plot that probably should have been done better. This is the current status of the field of exoplanets discoveries, including all kinds of detection techniques. On the x-axis, you have the orbital period in days. On the y-axis, you have the size of the planet in Earth radii. And the colors indicate both confirmed planet candidates and all Kepler planet candidates. Well, confirmed planets and Kepler planet candidates together. Just to give you an idea, there is I'm going to show here, there's a 1 Earth radii size and a 10 Earth radii size, which is a Jupiter-sized planet, roughly. Most of, no, that's okay. Much better. All right. Thank you. Sounds good. Thanks. All right. So you can see most of the discovered planets until now are between the 1 and 10 Earth radii sizes, between Earth and Jupiter sizes planets. And this is not a coincidence because many of our detection techniques are generally sensitive to these large Jupiter-sized planets, whereas, but then we don't find many of them because there are not many Jupiter-sized planets being created in our galaxy. At least this is the sample from our galaxy. But you can see there are many Neptune size and Uranus size, and some of the planets between 1 and Earth, 2 Earth radii. These are the super Earth and sub-Neptune planets that we don't have any equivalent in our solar system. They are the most common planets in our galaxy right now. And so if we want to look at the planets that we would be interested in, something close to, if we want to observe the habitability, then we need to know what kind of stars they are around. So one thing that this plot is missing is the stellar information. And so just because a planet is a 10-day orbit in this plot doesn't mean it is not in a habitable zone. So it depends upon what kind of a star you are around. And you can see I roughly plotted what are the typical, oops, I should go back. How do I go back?
The big red button goes back.
Go back. Oh, there you go. Thank you. So I roughly plotted the habitable zone orbital periods for spectral classes for M, K, and G. And you'd see that the width of the habitable zone for M-DWARFs in this log plot is wider compared to the G stars because the orbital period range for the habitable zones for M-DWARFs span an order of magnitude because of the very low spectral M types to the early M types. And many of them, you can see there are several of them in this plot that are Earth size or Earthish size within the habitable zones of M, and some K dwarfs. And there are some also around G dwarfs, but that doesn't mean that they are in the habitable regions. There are other factors that come into play to determine the habitability of these planets. And so that's what my talk hopefully will convey, that how important are these habitability indicators and how we can observe them, particularly around M-DWARFs. Okay. So to give you an idea, this is the list of habitable zone planets that I maintain on my website. And these are the all confirmed habitable zone exoplanets to date since the discovery of the first exoplanet that was announced back in 2007, that around GJ 581d. That was the first exoplanet in the habitable zone. So just to explain you what this axis is here, the x-axis is the amount of starlight on the planet relative to the sunlight on the Earth. So when you see 100% here on this plot, that means that the planet is receiving the same stellar flux as the Earth, the current Earth receiving right now. And so if you see a 75% of starlight, which means the planet is receiving only 75% of the starlight that Earth is receiving from the sun. And the y-axis is obvious. It's the stellar temperature. You can forget about the lines here, but what I want to show you is that the middle, the blue shaded region is the most conservative estimate of the habitable zone. And from this plot, you can see most of the confirmed exoplanet, terrestrial size exoplanets right now are around lower mass stars, the habitable zone planets. And there is a size limit that I put a cutoff for, starting at 0.5 Earth radii to 1.5 Earth radii. And the reason for that is that beyond 1.5 Earth radii, we think that the planets accumulate hydrogen and become a little bit less dense. And there is also a trend right now. There was a paper published last year or a year before where you see in the planet distribution that you see a dip in the radius of the planets at 1.75 Earth radii, showing the demarcation between what is considered to be a terrestrial planet and what is a planet that is a little bit larger. And so, yeah.
The planets that are to the right of the quote-unquote Fulton Gap,
Yeah.
Is that a theoretical construct that whenever planets are larger than that, they must primarily be gaseous? Or is it an extension of our solar system analogy?
So it is both a theoretical construct and an observational data point, because it was predicted. To repeat what Karthik is asking, there was a paper 2 years ago when they analyzed the Kepler data, and if you plot the planet radii distribution, starting from 1 Earth radii to, let's say, 10 Earth radii, the distribution increases and peaks around 2 to 3 Earth radii. But then there is a gap between 1.75 to 2 Earth radii. So you see a rising peak from 1 to 1.75, and at 1.75 it drops down, and then again it rises up again around 1.85 or 1.9 Earth radii. So what Karthik is asking, whether the gap between the 1.75 and 1.9 Earth radii, is it a theoretical construct or just an extrapolation from what we don't see in our solar system? So it was actually predicted. This gap was predicted in theory, and then they observed it in the Kepler data. And the reason for that gap apparently is because the evaporation of these planets, larger planets, going from larger sized planets to smaller sized planets, because the Kepler data is all, the one that I showed you before, is all constrained within 100 days of orbit. And so there are a lot of closing planets that are losing their atmosphere because of the close distances they are. And so those larger sized planets are losing the atmosphere, and you can see this distribution going from a larger planet size to the smaller planet size. So while transversing that, from larger size to the planet size, you don't see many of them in this gap, and that's why you see 2 peaks, because that is the transition region. The gap that you see is the transition region where planets are going from larger size to smaller size.
By the way, Earth, I think, should get 100% somewhere, right?
What is that?
I think Earth is sitting at 95.
No, it is at 100%. It's a visual thing. You failed the test, right? But so this is I plotted also the current solar system planets in this. These are the current habitable zones. So this is interesting that we can think about. At one point in time, there were probably 2 or 3 potentially habitable planets in our solar system, because Venus probably might have had water at some point, maybe lost its water due to runaway greenhouse. And Mars at least shows some water features right now. So probably around 2-3 billion years ago, maybe there were 3 habitable planets within the solar system. And right now we have only 1. And so that gives a hope to some of these exoplanets, but we don't know anything about how the habitability evolves around different kinds of stars. And so what we want to study is to look at the closest M-dwarf habitable zone planets. And this plot probably Kara already showed and talked about it. And so you know why M-dwarfs. We know they are 70% of the stars. They are small and dim, higher transit. You know, you can get short period planetary orbits. And there are more recent discoveries that are more amenable for observations. Kara pointed out Proxima Centauri B, which is not a transiting planet, but you know, you can probably get some sort of a phase curve observations, which we'll come back to later. TRAPPIST-1, one of the most famous one. The Tigardin star is the newest one that came out 2 days ago. So there was this paper that came out, you know, they found 2 planets in the habitable zone or near to the habitable zone of an M-dwarf star. So there is another reason why we want to study these M-dwarf planets, because there are some potentially observable climates that we can look at these M-dwarf habitable zone planets. And that's what I'm going to focus on in this talk. Like, how do we observe these climates with around these M-dwarf Earth-sized planets? Let me see if I can go. So one caveat that whenever I think of habitability of M-dwarfs, this picture comes to my mind. The reason for that is M-dwarfs are very active stars. And so there are some studies and some people think that it is hard for planets around M-dwarfs to retain any atmosphere, forget water, but any atmosphere at all. And so the first thing that we want to do is to see if M-dwarfs have atmospheres at all. And one of the things that we can potentially look at is to look for high mean molecular weight atmospheres. If it's a hydrogen gas, it's easy to escape. So we need to look for more higher mean molecular weight gases like carbon dioxide or oxygen, for example. So that's what we want to look in these spectral signatures. So one of them important things that one has to remember when we are talking about the habitable zone planets or M-dwarfs is that these planets are supposed to be tidally locked or in synchronously rotating, which means the orbital period of the planet is same as the rotational period, just like our moon. So one side of the planet is always facing the star. And the habitable zone orbital periods are between 4 days to 100 days, depending upon what subspectral type of M-dwarf you're looking at. And so, which means that these planets are not only their orbital periods are in those couple of days, their rotational period, which means a day there is probably 4 days at the minimum and 2 even longer ones. And so this slow rotation causes some unusual climate behavior that we don't see on Earth, and we don't have an equivalent here. And so to do that, that's what we use some 3D climate models to study these complex behavior of the climate dynamics and see how it impacts the observables. So that is what I'm going to talk in here. Like I said, so it's a global climate, right? So the Earth and planets are all 3-dimensional objects. So we have seen in some of the talks and even other talks that we have a spectra of an Earth-like planet and around an M-dwarf, which is fine. But M-dwarfs have several issues in the sense that they, like I said, they have slow rotation. So if you want to look at tidally locked, synchronously rotating planets and want to study the climate observables, then we probably need to look at these higher dimensional climate models and see how they affect the observations. And so this is the only slide I'm going to talk about what exactly is a GCM. It's called a global circulation model or global climate model. All you have is a one-dimensional column along the, in a simple way, a one-dimensional column atmosphere at a given latitude, longitude point, and then you have that around the globe. And you have a dynamical core, a central core, where it solves equations of fluid transfer so that you have how the atmosphere moves from one latitude, longitude point to the next one, and how the atmospheric dynamics changes around the whole grid. And so essentially, broadly, this is what we do in any global climate model. Global climate models have been being used for Earth system anyway. There are several global climate models, and if we want to study the greenhouse warming of Earth, the climate change, there are several models they have to agree together so that there's a consistent comparison and a consensus on how the climate system is varying. We have a similar project that's going on for exoplanets too. We have several global climate models we are trying to use and get a consistent and a consensus among the exoplanet modelers to see if they all agree in terms of what we can observe. These have been used to study hot Jupiter planets. Hot Jupiter planets are these are Jupiter-sized planets around very close to the stars, right? And they even made a longitudinal maps using these GCMs and matched them with the observations, where they predicted that the superrotation advects these heat and energy from the substellar point. Substellar point is the point where the sun is directly, or the star is directly having its instant light. And you can see that this super rotation, because they're very close to the star and they're rotating very fast, because the orbital period is same as the rotational period. Some of these hot Jupiters are less than a day in orbit. And so this super rotation advects the heat from substellar point to the other side, to the night side of the planet. And you can see this variation if you make a longitudinal map as the planet goes around the star. And this validates some of the climate modeling and would be important to do a similar analysis for habitable zone planets around M-DWARFs. Now, how do we do that is the topic. So what we do is we try to simulate these planets given a stellar spectral type. We input a stellar spectrum of M-DWARFs. We do not have any Earth-like assumptions in the sense that we do not assume a one-day rotation period. The spectrum that you all see in some of the studies is assuming an Earth-like spectrum. An Earth-like spectrum means that it's an Earth-like rotation period. So there are things that change when you change the rotation period. And that's what we want to see in these 3D climate models. Just to give you an idea, here is how does the slow rotation affects the climate, and I'll come to the observables in a minute. So the top one is a one-day rotation period, like Earth, and what these blue globes are showing are the cloud distribution, the water cloud distribution. When you see it from the front of the star, and that's the back of the star, and that's for one-day rotation. This is for 4-day rotation. That's around a planet, around a star with 2600 Kelvin, roughly a TRAPPIST-like system with the 4-day rotation. And this is around a star, mid-K dwarf, with an 85-day rotation period. You can see the cloud distribution changes, the water clouds. What happens is that as you go to slower and slower rotations from 1 to 4 to 85 days, the clouds tend to concentrate around the substellar point, and then they start increasing the albedo of the planet. And these clouds actually tend to increase the albedo and sometimes cool the surface of the planet. And so you can actually see this cloud distribution if you can do some orbital phase observations in the thermal emission. I'll come and show you that in a minute. But this is the effect of the cloud, the slow rotations on the cloud distribution on the exoplanets. And we can potentially observe them if we have enough sensitivity to resolve these water vapor features. So why is there, what exactly is happening? Well, if you have a one-day rotation Earth-like planet, what I'm showing here is the latitude on the x-axis. I know you can't see this here. Latitude, no, that's the longitude on the x-axis, and the y-axis is the altitude, essentially, surface to the top of the planet. In the one-day rotation case, and the colors bar represent the water in the atmosphere, okay? And so you can see on the one-day rotation case, there is a banded formation along the planet, similar to what you've seen in the previous plot. But as you go to a slow rotator, like a TRAPPIST system, like a 4-day one, you can see some water is already up in some part of the atmosphere. But when you come to an 85-day slower rotation, you can see that water is being uplifted and pushing up in that upper atmosphere. And if that's happening, we should be able to see that in our observables, right? And remember, this is at this is the substellar point, the middle of the point. These are the longitude, yes?
would you still see the large columns of water and clouds right over the substellar point?
So land distribution definitely affects. These are all aqua planets, as in completely filled with water. So we have some simulations that actually show similar behavior. So the land distribution does affect how much water you can get into the atmosphere because there are barriers that won't let the water go into there. But there is the reason why you see this water going up as you slow down is because of the Coriolis force. It becomes weaker. So for Earth, for example, the Coriolis force is stronger, and that's one of the reasons why we see hurricanes in the Gulf of Mexico, turning off and going into the Northern Atlantic, right? And so that Coriolis force is weaker for these slow rotators, and so all that clouds and water vapor concentrate at the substellar point, and that's why you see that. Okay, so if so slow rotation can push water vapor up into the stratosphere, then that would be an interesting case to see for some of these exoplanets. So one of the most famous one and the most important one for habitability test is this TRAPPIST-1 system because it has a good K magnitude that we can observe with JWST and also with origins. And so, see, I used origins, not OST. There you go. So I'm listed here the orbital periods of these alphabet planets, B, C, D, E, F, G, H. And the ones that are potentially in the habitable zone, that we think are in habitable zone, are E, F, and G, and these very close to the inner edge of the habitable zone. And if someone is talking about habitability of the system, most likely they'll be talking about the planet E or F and G. F and G are supposed to be colder planets, and E is supposedly, in the right region of the TRAPPIST system. And so there are some modeling efforts that have been done for TRAPPIST-1e planet. And so the top plot, I'll explain to you in detail about the spectral features. The top one is from a 1D climate model, including photochemistry. And the bottom plot is from a 3D climate model, including photochemistry. So both of them have a climate model and a photochemistry model included together. And so on the x-axis is the wavelength in microns, 1 to 20 micron, and the y-axis is on the top plot, it's the transit depth in parts per million. Here also it's parts per million, but it's plotted on the other side. These two studies, unfortunately, did not use the same axis, but I'll try my best to show you how it can be done. The most important thing, the prominent thing that you will notice here is the CO2 feature. If you see a CO2 feature, that means the planet has an atmosphere, right? So one of the important questions that we want to answer for planets around M-DWARFs is that if they have an atmosphere at all in the first place, because they are very active. And so is the atmosphere going, particularly for these smaller planets, TRAPPIST-1e planets, the atmosphere can quickly go just like that. And so if you see a CO2 feature, then probably the planet has an atmosphere. But there are also some other gases included here, methane and water vapor and so on. They are a bit little difficult to observe, but not impossible. However, if you include clouds, that's a different ballgame then. Because you see, on the bottom plot at least, here is the blue. There's a blue spectral curve. That's including clouds when they generated the spectra. You can see when you compare between, say, for example, the water feature here, the black one, and the blue one, the spectral features are completely shortened, which means that it's really hard to see these important habitability indicators, water vapor, methane, and all, if you have clouds on this one. This is reality. I mean, this is what the exoplanets give us. And so we have to take that. And so we have to think about how we can measure this using origins. And this is, so Thomas Fauché is the one, he was a postdoc in our group. This paper is in review now. So what he found out is that you need several tens of transits with JWST to detect these features at 1 sigma or 5 sigma level. And so it's a really tall order for JWST to actually do this kind of very tiny spectral feature observations. So why do cloud? This is all transit spectroscopy. Did I not say it? It's a transit spectra. It's a primary transit spectra. It's primary spectra. Right. So when I say transit spectra, the planet it's a primary spectra, right? It's primary transit. So the secondary one is called eclipse spectra.
It's emission, yeah. Secondary is emission.
Yeah, Yeah, I'll come to that emission spectra in the next couple slides. I mean, you know this, so yeah.
Yeah, no, I really honestly asked. I didn't know whether.
Right, absolutely, no problem. So this is just the transmission spectrum. When the planet is passing in front of the star, that's when you see. And
roughly how much are each of those features attenuated by when you have no clouds, a clear sky versus
okay. Yes, that's an excellent question because in fact there's a table in Thomas' paper that actually mentions these numbers. In terms of the ppms, they're reduced by half completely. In some cases, in the weak features in the near infrared here, it's even worse. So, and that too, this is all Earth-like atmospheres. Again, we used an Earth-like composition. So this is assuming Earth-like rotation, but using an Earth atmosphere. The same thing for the 1D model as well. For the Earth-like atmosphere composition. Rotation, they don't have a rotation model because 1Ds cannot do rotation. So you can do it with the 3D model. So both of them use the same composition, and they get some results match, some spectral features match. But in this case, in the 3D model case, you can see the water vapor. It's more moist higher up in the atmosphere, just because we talked about how slow rotation pushes up the water. So you should be the water vapor signals are slightly better for this one, but then clouds just kill everything. Okay, so why do clouds kill everything? So, well, if you have an extended atmosphere, for example, like a hydrogen atmosphere, its light can pass through because it has a larger scale height. And so an extended atmosphere, you have, when light passes through it, some gases in that extended atmosphere absorbs the light, and then you see that in the spectrum. But when you have a planet with a very high mean molecular weight, like for example, water vapor. So water vapor's molecular weight is 18, whereas hydrogen is 2, right? And so when you have a higher mean molecular weight, gravity pulls it, and so you have the atmosphere more closer to the star, or more closer to the planet's surface, and so the starlight passes through very little atmosphere, and so you would not be able to see many spectral features. Same thing happens with the cloudy atmosphere. When the clouds are blocking, you wouldn't be able to see these spectral features clearly. And so the clouds or high mean molecular weight atmospheres are really the enemy for, oh yeah.
Just one other thing, there's another effect too, that you get the light refracted. Basically, you don't see it at all.
Right. So.
Except at the really high, thin, tippy top of the atmosphere. So.
Right. This is particularly important for M-DWARF planets, where the planets are pretty close to the star, and then we can see the light gets refracted through the atmosphere.
We don't even see it other than at the very high levels.
Right. So those are the real problems that they show up in the spectral features. So what the summary of these things, of all the slides that I've shown you before, is that clouds can really destroy some of the, or reduce the spectral features. And so if you have a runaway greenhouse climate, for example, if you see Venus 1 billion years ago around another star, would you be able to see, what kind of an atmosphere would you be able to see? Right now, Venus is dominated by CO2. So when you see Venus spectrum, there's a good CO2 spectral features. You can see that. So when you see Venus around, when it was in a runaway greenhouse climate, dominated by water vapor, how would you see it? If the clouds are blocking it, how would you know what's happening there? And if they are completely flat? Well, this was a question asked by Carl Pilcher when an undergraduate was working with me, tried to show this plot with the runaway greenhouse spectral features for the transit spectroscopy. So how do we identify runaway climates if clouds are masking the transit spectral features? So there is potentially a good chance that many of the exoplanets that we are looking are going to be cloudy atmospheres. And so that's where the thermal emission spectroscopy comes into picture. Oh, I'm already over my time. And so if you have this phase-dependent spectra of these planets, you can actually see these in different wavelength bands. At least I'm plotting here from 5 to 20 micron and 10 to 20 micron regions. If you observe phase, you can see that there's a much higher chance if you go to longer wavelengths, 10 to 20 micron, you get a higher FP or planet to star flux ratio. Those are the broad bands, but this is the spectrally resolved secondary eclipse thermal emission spectra, and you can see that beyond 10 micron, you can get a lot of contrast ratio for these habitable zone planets around, this is for, again, a TRAPPIST-like system. And so what I would like to show is that, the spectral features I've shown you before do not have all the habitability indicators and biosignatures, but once we include them, you would see structure in this spectra, and then you would be able to see that in probably measurable quantities beyond 10 micron region. And that's where I think OST would definitely help. I'll skip this one and leave my take-home points here, that there are no difficult questions, but there are difficult answers here. Thanks.